All right, everyone. I have a couple minutes after 9 a.m., and it's really important that we use all of our time this morning because this could lead to a lot of discussion. This is going to be very different than any session that you've experienced in the scientific conference this week. Our intent and purpose here today is to have a discussion with you. So we want to talk about our radiation background measurements that have been conducted to date, talk to you about our noble gas systems, and I have on the stage here with me the experts, and I will introduce them to you and our extended team in just a moment. But what I want you to understand is that we're going to take your questions throughout, but because we're going to have a slide deck in front of us on the stage, we're not going to be seeing questions that might be streaming in through the mobile app. I'm going to try to keep an eye on those, but they will be completely visible to us as a team once we get through the entire presentation. If you want to make a comment, a recommendation, or ask a question, if you could stand up and make your way to the front of either side of the room, there will be someone available to give you a microphone to be able to present that question. We would greatly appreciate that. We want this to be as interactive as humanly possible. Don't be surprised if we don't call on someone in the audience that we feel knows more about a question than we do particularly. So to my right, I have Martin Kalinowski. He is the unit head of scientific methods. Hakeem Gadoo is our radionuclide officer in software integration in software applications section. Next to him, we have Pierre Bourgon, who is an ATM expert, and Pierre had a really unique role during the DPRK tests that occurred. He actually sat in the director's office as an advisor, the IDC director's office. And then next to him is Jolanta Kuzmierczak-Miszulek, and she is also an ATM expert. So thank you all for joining me this morning. We have an extended team of experts who have been helping us back at home. I want to acknowledge Jonathan Barre, Guillaume Bizet, Idrissa Udrago, and Noako Inoue. With that, have I missed anything? We're good. Okay. So let's get started with our slide presentation. I want to emphasize the point. I borrowed this slide from Okal from a presentation he gave yesterday. We are a group of scientists trying to make a presentation to policy and decision makers. And so you will see us wanting to get deeply in the weeds, make points about things that might be confusing, just driving home the point that we really need your assistance to bring us back to the level that you need us to be, to answer all of the questions that you have. And unfortunately, with the lighting situation, it is a challenge for us to see your raised hands. So again, please come forward so that you can ask your questions. Next slide. So we have 4 chapters of material that we're going to be presenting to you, and each one of us will help you get acquainted with us and our skill sets over the course of the next hour and a half. There's 4 major chapters. The Ims Noble Gas System, its purpose and the experience that we've had, and I'm going to walk you through that. The DPRK experience itself, Pierre and Jolanta, for the most part, are going to present those results. The Mobile Noble Gas Measurement Campaign, Hakeem is going to walk us through a bulk majority of that, but like I've shared already, we're going to be going back and forth between each other and playing off of each other, and then I'll close us with the future work. So Martin, yeah, let's get started there. Just a reminder to everyone how we got to where we are today. The Conference on Disarmament, starting in 1993, actually laid the foundation for all of our technologies, including the radionuclide and the noble gas. So if you advance forward on that, just a reminder of what that looks like. So once we got into the negotiations, the part of this slide that's relevant is that relates to the underground testing. And we had a requirement of 1 times 10 to the 14th becquerels of xenon 133 in a 12-hour release, no particulate debris, and 10% of a gaseous debris is released. That's the assumption of the scenario posed by the Conference on Disarmament. And so the probability of detection needed to be greater than 10% within 10 days of a 1 kiloton underground nuclear test as defined by the Conference on Disarmament. So that's how we get to the numbers of measurement. Now we turn to our draft IMS operations manual and the requirements that are laid out within that. We have 4 isotopes that are specified: xenon 133, which we've already talked about, 131M, 133M, and 135. And another material point on this slide is the minimum detectable concentration, and that's less than or equal to 1 millibecquerel per cubic meter of air for xenon 133. That's the only isotope that is specified with a minimum detectable concentration. And we hope for you to understand in the context of this presentation that that's good. That's the good xenon isotope to be looking at in terms of these measurements. So now we can go back to the next slide, which is our Ims Noble Gas Network. So you're used to seeing the globe covered with all of our network capabilities. This just specifies those that have noble gas capabilities. And it's a little bit small in text to differentiate between those that are operable and those that are still under construction. So there's a total of 40 once the system will be built out. As was emphasized by Petra during the DPRK panel earlier this week, once we enter into force, then the global community will have the opportunity to decide if those 40 are enough or we need more throughout the rest of the radionuclide particulate stations. So we have 5 noble gas stations that are under planning, 2 that are under construction, and all that are installed are certified, and the total number of those is 33. Next slide. This gives you a portrayal of what we call legitimate sources of radioxenon, and legitimate are really those that we understand and are not associated with a nuclear test. So you can see our IMS stations. This is the total stations that will be deployed, and 33 of those are active. The red X's are the nuclear power plants around the world. The orange squares are the research reactors, and the blue X'd boxes are the isotope production facilities. And you can see that there are very few of those. But as we know, and you will hear again today, they're strong contributors to that global background radioxenon. Next slide. These are our civilian sources of radioxenon that are causing that atmospheric background concentration of radioxenon. So these are sources of information that we are beginning to understand. We don't fully understand. Can you click on the lower left? Thank you. So this is the average background of xenon 133. This was over a 3-year average time period. And you can see that in the northern hemisphere, there are high concentrations centered around coming off of the United States. This is primarily from the time period that Chalk River was in operations. And if you were to combine that with the information that you just had in front of you about where the medical isotope production facilities were, there's a very strong correlation. Does anybody else on the team want to say anything about that graph before we move on? That's fine. Okay, good. And then hit rates above the detection limits. What you have in the legend at the bottom of the screen is the number of days per year that releases are detectable. And at the very high range, the dark purple, it's 250 to 350 days per year. And at the very low end, where it's white or very light green, you're kind of in the 0 to 20-day range that you have any hits. So again, this emphasizes the point that the previous slide did. And it begins to help you understand that that background is present and persistent in those regions that are the dark purple shade. Next slide. Okay. We'll make a transition now over to Hakeem, giving you some background on the Noble Gas Categorization Scheme, something that he helped us create.
Yeah. So good morning, everyone. So noble gas is actually, compared to particulates, relatively new in the CTBT operations. The very first certified systems have been promoted to IDC operations in 2011 when the new software has been deployed. Then 1.5 years later, we implemented the categorization scheme for particulates, and this is a 3-level based concept. Level A, if there is no detection. Level B, in case we have a detection, but the activity concentration is within the typical range for the station. And if, in case of abnormal concentration, the sample gets categorized to the highest level, which is level C. In addition to that, the IDC products are also providing information for event screening, and this includes the isotope ratios and the data quality flag. Something which was also discussed and approved by Working Group B was to provide information on the atmospheric backtracking based on known sources. Next, please. Then here we have the overall picture since noble gas categorization was deployed in the IDC in September 2012, and the data are up to the 31st of May, which corresponds to a total of more than 80,000 sample spectra that have been automatically processed and then interactively reviewed by IDC analysts. And the pie chart now shows the overall results in terms of distribution versus category. As you can see, 50% of the samples are green, which means with no detection. Then the level B in yellow is 42%, and we had 4% of reviewed samples at level C, which makes it a total of 46% of the samples have detected radioxenon, either at level B or level C. Next. So here we see 3 typical situations for the abnormal threshold that we are using for categorizing at level C. And this is for the DEX 33, which is a station in Freiburg, Germany. USX 75 is in Charlottesville, USA, and the Takasaki station JPX 38. So what we see from this plot is that first of all, the abnormal threshold is quite stable for Takasaki station. For Germany, it is a bit, we see more variability, but compared to Charlottesville, where we have the highest variability. And on top of that, if we compare this against the minimum detectable concentration, which is 1 millibecquerel per cubic meters, we see that only JPX 38, Takasaki station, has an abnormal threshold below this minimum requirement. In other words, if we only look at level C spectra for Charlottesville, for instance, so Some of them will be 4 times higher than the abnormal threshold. Here we see a typical time series of xenon 133 abnormal threshold at Charlottesville, and starting from late 2016, after the Chalk River was shut down progressively. Then here, the y-axis is the xenon 133 activity concentration. We have the green dots, which correspond to non-detection. The yellow squares are detection, categorized at level B. Then the red dots are abnormal detections. And this is in logarithmic scale. So from late 2006, we see a clear decrease in the activity detection, but also in terms of detection frequency. And this is showing a clear impact of a medical isotope production facility. Now here, this is the typical distributions for the 3 stations: Charlottesville, Germany, Freiburg, and Takasaki. So Takasaki station.
No. Takasaki station.
Yeah. So here we see we zoom in at Takasaki station, where we see a lot of level C episodes detections here over years. And this is since the station was certified in May 2014. Next.
No. You want to give?
Okay.
It's okay?
Yeah, please. Yeah. So now we will see the animation of 16 years of detections at IMS particulates
How do I start?
stations.
Ah, here. Yeah. Thanks.
Yeah. So here, green or blue means only natural radionuclide have been detected. Then if we have a CTBT relevant detection, the color turns into red, and the size is the activity concentration is mapped into the circle size.
Fukushima is coming.
Yeah.
Yeah, now then, at March 2011, we see the Fukushima Fallout and how this has been detected at IMS stations in the whole northern hemisphere
It's over.
over 2 months and a half.
Shall we go through? No, it's enough. Next
Is it?
slide. Shall we continue?
Yeah.
Okay. No.
Okay, now this is the animation for noble gas detection since 2011. And as you can see here, we have stations in the Charlottesville and in the US and St. John's in Canada, but also the station in Stockholm, Sweden, the one in Spitsbergen, Norway, which are detecting xenon in a very frequent way. And this is due to releases from severe sources, including medical isotope facilities and nuclear power plants. Then Takasaki Station since June 2014, when it was certified. And then we have the station in Melbourne, Australia, which is also detecting from Sydney, the ANSTO medical isotope facility in Sydney, also Darwin in the northern part of Australia. So this shows a clear correlation between xenon detections in terms of frequency, but also activity levels, versus the location of the major sources for xenon in the world.
So, Hakeem, before we move on from these two graphs, we've just seen a global map of the operations of the particulate radionuclides and compared it to the Noble Gas Network. I see a lot more activity in colors here.
Yeah.
What do you have to say about the major takeaways and differences between the two in terms of what they're seeing?
Yeah, thank you, Tammy. Indeed, this is one of somehow the outstanding issues. If we compare the rate of the highest level for noble gas, which is level C, we have something like 4%, which means we are seeing a level C once to twice every day in the average. Compared to particulates, the rate of level 5 is only 0.2%, which makes it a ratio of 20, which means we are seeing 20 times more frequent abnormal detections for noble gas compared to particulates. And then this means that the categorization scheme needs to be looked at just as a first screening layer. And in addition to that, we have the isotopic ratio, but the issue there is that we are not detecting very frequently all xenon isotopes. I mean, it's only in a few cases that we see at least 2 isotopes so that we can look at the ratio. So this is to put on the side of how challenging is the analysis and the use of radioxenon detections for CTBT verification.
Okay, thank you.
I can add on this.
Please.
Yeah. So let me also point out what the important fact here is. It's not only about the question of how many noble gas detections we record. It's also about, whoops, this is not enlarged, unfortunately. Yes, it is. Okay. So this I want to blow out and refer back to the Charlottesville station. And here you have a distribution of the concentration. So what I want to point out is that the red detections, which are 17% at this site, are at a fairly high concentration because of the abnormal threshold. This red line here lies always above 2 millibecquerel per cubic meter. That means that all yellow level B normal detections, normal background, many of these are above 1 millibecquerel per cubic meter. But please remember, 1 millibecquerel per cubic meter is the minimum requirement for a signal from a nuclear test to be detected by the Ims system. The Ims system at Charlottesville has a much better sensitivity that you can see here. It's 0.1. It's 10 times better than the minimum requirements that was derived from the treaty negotiations design criteria for the Noble Gas and the Particulate network. But in this range between 0.1 millibecquerel and the abnormal threshold, above which we call something alarm levels C, in this range there are a lot of observations, as you see from this histogram bar here. But many of these are above the signal that we need to detect and understand. Yes, we detect all these signals. This system is good enough, but the IDC analysis methodology is not yet capable of distinguishing whether these above 1 millibecquerel per cubic meter detections are coming from civil sources or a nuclear explosion. And in the past, when there was an announced DPRK test, most of the time, the experts focused on level C detections and ignored most of the time the level B detections, simply because it's much more complicated to try to understand the source of level B detections. And it is already quite difficult to understand even the abnormal detections. And this will be discussed now in the next part of our presentation.
Yes, on the DPRK. Well, Martin is moving to that chapter. We have a question for you, Hakim. How often do the Charlottesville and Freiburg stations detect signals likely from medical isotope production? And would the station be useful for detecting an underground nuclear test on those days? It ties deeply into what Martin just said.
Can you show the question on the screen? Thanks.
If we look at the detections that we have seen at Takasaki in April 2013, after the DPRK nuclear, 54 days after the DPRK announced the nuclear test, the activity concentration of xenon 133 was only around, the highest one was only around 2.4 millibecquerel per cubic meters, which actually falls within the detections from the civil sources, which means if we only look at the levels of activity concentration, then what we would expect from underground nuclear tests will easily fall below what we are detecting at the IMS stations, including Takasaki, Charlottesville, is where we had actually the record in terms of activity concentration up to 140 millibecquerel per cubic meters. Then what helped was actually the co-detection of two isotopes, which means xenon, which were xenon 133 and xenon 131M. And then it was the isotopic ratio that allowed to make good use of the detections and cross-check for correlations in terms of event timing and event location against the signal from the seismic data, which means the background from civil sources is enhancing the background at IMS stations, and expecting detections at higher concentrations is almost, I would say, unlikely to happen from underground tests. This is another fact to be taken into account, is that the activity concentration levels that may come from nuclear tests will be rather very low, and in many cases much lower than the background.
Okay. So masked by that background, essentially. Okay, back to the DPRK.
Okay. Tammy mentioned a few times the importance of the radio xenon background. Hakim showed that there are many detections at level C and some at level B. So what happened during a test or the days following a nuclear test? So this shows the activity concentration in millibecquerel per cubic meter from August 3rd to August 7 about. And what you can see immediately is that there are a few very high episodes, like around 3 millibecquerel, 2 millibecquerel. And we mentioned that our system is tuned to detect something like 1 millibecquerel. So how do we deal with these detections? Because also you have to remember that the background is not a static thing. The background is caused by multiple different facilities emitting on their own schedule. Facility A can emit a lot on Monday, facility B on Thursday, and so on. And also there are the weather conditions. And so everything comes together to produce a very a background which varies quite a lot day to day. So if you observe a peak, is it from normal background variation, or is it from a detection? So I guess that's the challenge. So all those peaks, as it is indicated, thanks, Martin, are from known sources. So that's the challenge. The background is not static. The background depends on the emitting sources and on weather condition. If we go to the next slide. This test in 2006, it was possible to identify, it was possible to have a clear identification of a real event in Yellowknife. Yellowknife is about, I don't know, 5,000 kilometers away from DPRK. And it took, I don't remember exactly, but something in the order of 2 weeks to cross Pacific. It is amazing. And still, our system was able to detect this test, 5,000 kilometers away 2 weeks after the event. And why was it possible? Maybe if we can go to the next slide. So the top graph shows the actual activity concentration at Yellowknife during that period of time. So, and the dark area at the bottom is the background. So, on the opposite of what I just said, in this area, the background is quite low most of the time and quite constant. So you see the background is in the order, I don't know, of 0.1, something like this, and very constant most of the time. Sometimes there are peaks, but not very often. So we have our detections, and what we see, a few peaks. So it's quite possible, but it's not quite enough. So we have to identify possible contributions from civil sources. So that's what we did. So in this area, that's northern Canada, northwestern Canada. In this area, the only major source is Chalk River, CRL. And what we did is we used our ATM capacity to estimate the background associated with CRL. And what we see is that during the major peak, the contribution from CRL was very low. And that way, we were able to say, okay, that's a real detection. And again, you can notice that the peak is at less than 1 millibecquerel. So it is better than the original requirement. So this illustrates the importance of background, the importance of estimating the background, and that our system basically works. And if we go to the next one, I guess this one is more for Akeem. You want to say a few words on this one, Akeem? Mm-hmm. Or Martin?
Yeah, could you step?
Is this the next one?
Mm-hmm.
I should talk about this. Oh. Okay, I can say a few words about the DPRK announced test of 2013. You see here a time series of the Takasaki station for 2012 and early 2013. And there are several level C. They are not marked in color, and marked in color are only the level C detections that were later identified as coming from the announced DPRK test. Actually, they were detected in May, and the test was in February, so they came about 50 days later. It was a late release, but what really made it possible to associate it clearly with the nuclear test and its time, the zero time, the explosion time of the nuclear test, is the isotopic ratios between xenon-133 and 131M. According to a plausible scenario, there may be other scenarios, but a plausible scenario for the nuclear tests, the isotopic ratios and the zero time determined from the ratios pointed exactly at the time 50 days, 52 days before the detection when the explosion took place. So in this case, there was not only a very clear abnormal threshold, above abnormal threshold signal in both isotopes, but also the isotopic ratio and the time derived from that pointed at association with the nuclear test. Of course, we also did atmospheric transport forward and backward modeling to confirm that the air that we received over these couple of days was in fact coming through the test site area of the PRK. And here is such forward modeling, but now we are turning to another announced test. It's the January 2016 test. So I pass over maybe to Jolanta or back to Pierre, it's up to you.
This is an example of animation, one of the animations that we do and analysis that we do during monitoring phase. So when the test is announced, what we do as atmospheric sciences officers, we check whether the hypothetical release from DPRK will be released by our IMS stations, and we try to monitor this. So this example, here is this animation showing the plume, and we see that there is a chance that the station Takasaki will detect. And this is another example of animation. It's from 2016 DPRK test. And also here we see the plume moving, and there is a possibility that Takasaki station will detect something. So in this monitoring phase, we are testing different hypotheses and are observing, and if to verify our hypothesis, we do forward modeling, but we also check backward modeling. So we trace air masses backward, and we check where the air masses were prior to the arrival to the station. So can we go to the next slide?
In fact, we go now from DPRK to the Takasaki station. The Takasaki station, I can introduce this slide, or Hakim, you can? Yeah?
Yeah.
Please do.
Yeah. So on this shows a frequency distribution for the 4 xenon isotopes at Takasaki, and this is over the last 12 months, from June to June. So here we see in dark green the level A, which means no detection. Then in green, it's green, light green to yellow is the level B. Then the red bars are level C. So what we get from this picture is that the level A and level B are actually sharing some activity concentration range. So if we look at the stacked bars of the two green and light colors, whereas the level C is rather on the right side of the activity concentration range, and this was a total of actually a few level Cs over last year. So here, it also shows how challenging is to distinguish between not level B and level A as well, taking into account that the detection limit of the systems is also varying from sample to sample. It's another aspect to be taken into account.
Jolanta, maybe you could emphasize for us what are the sources of these detections?
So here is the slide which illustrates how many different type of civil sources can contribute to the detection. So, for example, for Takasaki Station, we see many different colors, and each color represents only the most powerful sources. In violet, we have indication the cumulative contribution from nuclear power plants. In other colors, as you see, there is this contribution coming from medical facilities. And this result shows the average contribution per month for year 2014. What is interesting to observe is that during the summertime there is a very strong contribution from nuclear power plants, like in July or August. Almost more than 80% the signal that is observed at the station comes from nuclear power plants. So to analyze the detection and to be able to see something more than the background, we really need to have a more accurate knowledge about the background. So
before we move on from that slide, maybe Jolanta or Martin, you could emphasize a point. This is over a very long period of time. What about and how do we account for single release events?
Sorry. No, this is it.
Okay, we mentioned earlier that the background is a rather dynamic beast, and it varies quite a lot. And this simulation just tries to illustrate this. What we did here is we take only two of the major medical isotope production facility, Fleuris and Dimitrovgrad, that you can see the black dot. If you're good, you will see the black dots on the map. And the colors refer to just the green is Dimitrovgrad, and the more colorful is Fleuris. So you can see, looking at this simulation, you can see that sometimes the two plumes will overlap. So of course you expect that this will create increased values. Sometimes over an area there is nothing, so background will be low, and sometimes this is a mix of the two. So this really visually shows how the background varies in time and in space, because often we think that the background is kind of uniform in the horizontal and in time, but it is not the case. Often the background is quite variable. So if we have more measurements, we can quantify this spatial variability.
So this is another example of animation showing a plume released from two sources, from one near sources of Takasaki and one remote sources from Dimitrovgrad. So those two plumes, one from a close source, one from remote source, they meet together at Takasaki Station, and then at the station we observe the detection, and this detection is kind of contribution, shows the contribution from different sources.
Okay, before we move on from JPX38, we have a question from the audience. Can any of you as experts explain currently what the knowledge of civilian sources is in this region and explain the decreasing trend of level C detections at JPX38? Go ahead, Hakeem.
So the question is whether we can currently, based on the current knowledge on civilian sources, explain the decreasing trend of level C detections at JPX38. Actually, I think this is something that we maybe didn't yet look at. And but to be also somehow taken into account that it depends if we look at the monthly detections like median or on a yearly median, but if we combine, we also have some seasonal variations at this station to be taken into account. Which means if we take a snapshot of 1 year, then indeed we see that we have lower frequencies, I mean less detections in some seasons compared to the high seasons. And I think, Martin, we did have some discussion on this case in the past, Takazaki.
I can add on this.
But a clear decrease in terms of frequency, in terms of activity, concentration level, I would say both need to be taken into account.
Okay.
Thank you.
So I can add on this. If you want to get an answer to this question, you need to know about the sources. And there is a good knowledge about which sources exist, civil sources, as Temi showed on one of the maps at the beginning of the presentation. But what is not so well known is the source strength. How much do these sources release per year? We presented at this SnT conference an update of our best knowledge from literature and openly available data, the release inventory of radioxenon. But currently this is, for a generic year, a total annual average of certain plants, and we collected these data for 2014. But we don't have information collected about trends. There may be information out there, but I say we didn't collect this. And if we would have more information about the release of radioactivity, of radioxenon from the known sources, then we could answer this question. Yeah. So in principle, we have the tools, as Jolanta and Pierre are demonstrating. If we do know the source strengths, then we can predict quite accurately the concentration that is detected at Takasaki, and then we can explain why we have less level C events in the past 1 or 2 years. And the simulations that they showed use the assumption of a constant release term, and only the wind conditions are causing the concentration differences that you saw. But you can modulate this also with the source strength, and then you get a much better and much more accurate prediction of the concentrations in Takasaki. And this is what Jolanta is showing in the next slide. It's the time series of her predictions according to atmospheric transport modeling. And if that is also modulated with the source strength information of the source with a stuck detector, then we can much better predict the concentrations at Takasaki. So Jolanta, if you want to continue with that, perhaps.
Can I have a slide?
Back to the presentation.
Yeah, thank you.
Okay, so maybe I will give it to Pierre because...
Yeah, okay, this is related to the same simulation we saw previously, just a few minutes ago, where we had 2 sources, Flores and Dimitrovgrad. And what now we're looking at is the contribution of those two sources to 3 different detectors. The top one is Takasaki, our regular IMS station, and the bottom 2 are Oronobe and Mutsu, 2 stations within the current campaign. And the idea here is, and it's a bit difficult to see, but if we look at only at the green line, the top line, the top line represents the contribution from the 2 sources.
No. Sorry. It's not everything hyperlinked.
Yes. And what you can see is, for example, at Takasaki, there is a maximum earlier than at the 2 other stations. And you can also notice, for example, that Mutsu is more sensitive to those 2 emitters. And what is interesting here is the point is those sources are in the order of 7,000 kilometers away, and those 3 stations are within, let's say, 1,000 kilometers. So even if the source is the sources are very far away, by adding a station, we can study the spatial variability and this is a clear example that it is not that uniform. And the next slide, please. The top, it's a bit small. Yeah, the top. Perfect. The top slide shows the average low-level wind for January. So if you can average everything in your head, which should be easy for you, you see that usually there is a westerly component is very important. So in this area, it is pretty much under the influence of everything going on to the west, so over Europe and over Western Russia. So anything released in this area has a good chance of ending up in our detectors in Japan. So this is the situation during the winter time. But as Yolanta showed just a few minutes ago, it is not the same during the summertime. During the summertime, winds are much lighter, and if you look at at Japan, you see that it is mainly from the southwest. So that's why the influence of medical isotope production facility in Europe and Russia is very low, and this explains the difference between the summer and winter condition. So it is very much dependent on the average flow.
Oh.
I think that wraps up our DPRK section, right, Martin?
Not really.
We have one more, maybe the long time series.
Yeah, let's go to this.
Yeah. Why don't we have you explain this one?
In fact, there is more. I'm sorry. The level C episodes.
Okay.
Should I take this? Mm-hmm. Okay. So whenever there was an announced DPRK test, analysts looked into level C episodes, and here, for example, after the 3rd September 2007 test, so 3 Septembers about here, and then you see a time series that starts with that date. And in the immediate time after the announced test, about a week or 2 after the test, there was only very low-level radioxenon at Takasaki. Still, there were a few detections, but it's hard to say whether they are coming from the DPRK test or not. Here, there's what we would call a level B episode, so it's a sequence of several detections that can be understood by assuming a single release. It's from a single source, that the enhanced plume that travels across Takasaki over a couple of samples, subsequent samples. And here are another few higher level Bs, but then there are 2 level C episodes of 2 successive samples, so 2 times 12 hours, a plume passed over Takasaki with elevated concentrations. You have seen before that we try our best to make information, to use information of known sources and predict the concentrations at Takasaki. In this case, this plot adds information from all known civil sources. These are the blue stars on the bottom of this time series here. And you can see that the blue stars sometimes indicate elevated concentrations, not just as high as the observed concentrations, but at least the pattern of how it goes up and then falls slowly back down to a minimum level may indicate that we may understand the source, which source it was, but we have underestimated its strength. But it may explain this level B episode here around 2021 September. But if you look at the level C episode here, then our known sources have not even a slight increase at the same time, according to constant emission assumptions that we have, because we don't have the real emission. So there may have been an enhanced real emission. Even the nuclear power plant can have 1,000 times higher emission on one day compared to what it has on a normal operational day. And then it close by, in the region, nuclear power plant can even cause a level C episode, but we don't know about these source strengths. Therefore, we have still to assume that any of the known sources can be the source of this detection. And then atmospheric transport modeling has to just trace back where the geographic region is, where this material might have passed over in the past and collected a plume, a fresh release. And similar arguments play out here, but here you may see some indications of risen expected concentrations. In these cases, we did more extensive studies. We looked into this example, and we did our atmospheric transport backtracking, possible source region analysis, forward field of regard and possible source region, because possible source region we can do only if we have more than one sample. And the nuclear test site falls into the possible source region, so it is consistent. This detection is consistent with the assumption that it does come from the DPRK test site, but other sources cannot fully be excluded. Therefore, it's not conclusive evidence. This is a statement that we often had to arrive at, that, yeah, possibly, maybe this was a release from the nuclear test site, but we don't have clear evidence that other sources can be excluded. If we would have more precise information of other sources, we could fulfill the mandate or the purpose of the monitoring network and make a clear decision, or state signatories could make this judgment. It's not up for the CTPTO to do this, but for the state signatories. But with this additional information, perhaps a better informed decision can be, and judgment can be made. For time reasons, I jump over the next slide and go directly to the long-term series. If you take a little bit more time and studies, 1, 2, or 3 years after the DPRK announced tests, scientists published more refined analysis results. And I give you here one example, and I highlight this example because this focuses not only on level C detections, but takes into account almost a month of time series of detections, and not only of one station, not only of the Takasaki, but also the Mongolia and I think it's Wake Island, USX 77. And in total 50 samples, some of them are even non-detections, and it does a minimum cost function approach to determine that the most likely source that can explain detections over this period of time is under this red or orange colored region. So the region that is the possible source for the most prominent detections in this period is quite limited if multiple samples over a longer time series are included with the more sophisticated method. These methods, this is one example in more alternative approaches like Bayesian approach and other approaches, inverse modeling and so on, they still need to be further tested and developed so that we can put this and NDCs can put this into their operations. Here's the time series that I was just referring to. So the study that we were looking at here used the data in the red marked area here of the Takasaki station. And in this period of time, from over 2 years, January 2016 to end of 2017, 3 unknown tests occurred. You see that the study that was done and that I just discussed was done for a period of time of fairly low concentrations at Takasaki. There are higher concentrations later, and there are even much more level C episodes. And we received one response or question according to the previous question why Takasaki level C episodes were more rare in 2017. And as Ted pointed out, yes, this may be due to Chalk River being shut down in this period of time. But we didn't look into this, therefore I didn't want to make this statement. But what you can also see is that after the 9th September 1916 test, there were very low detections and concentrations in Takasaki, but Pierre and Jolanta explained that this comes because over the summer period, the air is blowing more from the Pacific and not bringing Eurasian sources into detection in Takasaki. And after the 3rd September 2017 test, we had comparatively higher level B detections and only a late level C detection after that test. So the point that we want to make here is that if we only focus on analyzing the 3% of level C episode and question every one of those, whether they may be related to a nuclear test, we don't fully answer the real question that we have to answer. And this is there any signal that may be related and can be explained by a nuclear test? We have to, the system has to be able to detect that. And the real detections may be occurring as level B. And level B at Takasaki is more than 50% of all detections at this station. So we have to take this rich information that the IMS system is providing into consideration and try to also understand half of their detections, half of their samples, and not only focusing on the 3% that are level C as we did and were confined to do after the announced DPRK tests.
Okay, before we move on to give you a summary of the Mobile Noble Gas Measurement Campaign, we have a couple of questions from the audience, and this one's very timely, so I'll ask it first. So Hakeem, you may want to answer this, or Martin. Did you consider the review of the currently used categorization scheme of noble gas and whether it meets the CTBT verification requirements? It's a lot of information there in that B layer, and so maybe that question is coming from that.
Yeah, okay, I can do this.
Yeah,
so
actually, before implementing the current categorization scheme, we first took the time to discuss among the monitoring community, I mean CTBTO, and the member states experts, and this took us something like a year and a half. Then I remember one of the very first ideas were to also include the isotopic ratio into the categorization scheme and then make it 5-level based, which means on top of the current scheme, there will be also level 4 in case we have 2 isotopes detected with an isotopic ratio within the nuclear test domain. than if we have all 4 isotopes detected within the nuclear test domain, then we would have a level 5. Then it turned out that we also have to take into account that as CTBTO, PTS, we have to work within our mandate. Looking at taking into account isotopic ratios in the categorization scheme will be somehow exceeding this our mandate and providing in a way the answer whether an event is a nuclear explosion or not. Then there was this agreement and consensus, and we implemented the 3-level categorization scheme. The very first version was not considering xenon-131M at the same level of importance compared to the other isotopes, thinking that detecting xenon-131M alone would not be significant, relevant in terms of CTBT verification. But then our experience from DPRK-related detections in 2013, we learned from that experience, and then the Noble Gas Categorization Scheme was revised in January 2014, so that xenon-131M is also allowed to trigger a level C, even if it is detected alone in the sample. Which means the categorization scheme is, as we mentioned in the beginning, is the first screening layer, and we are learning a lot from our experience with the data from both the IMS systems, but also the mobile campaigns. Maybe Martin, if you want.
Okay, I would like to go back to the slides and show you again the categorization scheme. Oops. No.
There it is.
Okay, so just to remind you first of what we have in our categorization scheme. When this was agreed in 2014? 12 already.
Oh.
So we mainly focus on this breakdown scheme, classifying every sample either as level A, B, or C. In fact, what it doesn't show is that we do this for every isotope, and then we derive the overall category for the sample according to what is the highest level of all isotopes together. So if any of the 4 isotopes is level C, the whole sample becomes level C. But this is just to be more comprehensive in informing. But the question is whether we were considering changes or enhancements. Anyway, the question goes to member states, but state signatories. But scientists also look into this, and I want to point out that in addition to these 3 levels, the categorization scheme also includes so-called flags. Because mainly what we are searching for are anomalies, or something as additional information that NDC analysts can use to make a decision. And the calling for a level C, abnormal threshold concentration, highlighting that is just a first indicator to look at. And I need to repeat my warning. It's considered to be the first indicator. But if only first indicators are looked at for further studies, then you miss the level B. I repeat myself, but it's very important. In addition, there are several flags that can also give relevant information about the character of the event if there is anything detected. The isotopic ratios, yes, one can look at the 4 isotope ratio plot, and it clearly distinguishes 2 domains, reactor versus explosion domain. But every single isotope ratio of 2 isotopes has information regarding this distinction between whether it is a nuclear explosion or a reactor or medical isotope production facility, which basically is also a reactor behind it. So these 3 isotopes were initially and are currently in all our reports, and it's a yes or no whether the ratio is higher, and then if it's higher, it indicates it's coming from a nuclear explosion domain. These flags are almost never risen. They are too, the threshold for this decision is, in my view, too high, and we did a study to tune this threshold to make it more relevant, and the studies need to continue because it was not yet agreed to implement results, but this is one way of enhancing the existing agreed categorization scheme. Also, there is ATM backtracking to known sources. This is a flag that was agreed we should put in our reports, but even though we are prepared to put it in, the confidence in this giving robust information is not good enough. So we cannot include this ATM transport modeling, backtracking indicates that the detection can be explained by known sources. As I showed you an example before, this doesn't work yet. We need better information about the sources to be able to implement what we were asked to implement, to complete our implementation. But we can do even more. As I said before, what the NDC analysts really need is abnormal, some indicators for abnormal detections. One of them could be if the source comes from a geographic region where there is no known civil source. And this, in my view, could be done with machine learning, because we have long time series of detections, and we have all the atmospheric transport modeling results. So every detection or episode of detections can be compared to past evidence, whether it fits a pattern that hints at the known locations of the sources. So in that case, we may do it even without knowing the source strength. And then if there is a release from a location that is sufficiently far away from known sources and has an impact on our stations, then the artificial intelligence, the machine learning tool would raise a flag and say, okay, this is maybe suspicious. So that is my answer to this question. Thank you.
Thank you. We can go back to the slide deck now on the mobile noble gas. Yeah, right there. All right. And Hakim, do you want to begin walking us through this, please?
Martin, is it the first slide?
Yep.
Yeah. So this is now about mobile noble gas systems. In terms of specifications, the requirements are the same than for IMS systems, which means they are designed to fulfill the detection, the same detection limit, and to demonstrate the same performance as IMS systems. In addition to that, and for transportation reasons, the mobile systems are encapsulated in ISO containers, and they are also equipped with additional power supply systems. Data transmission is done by emails. Technically speaking, we are using the same messaging system, but the difference is that the noble gas IMS systems are processed and analyzed in IDC operations, whereas mobile systems are only processed in like an offline pipeline, which is the IDC testbed. So here are also more specifications in terms of infrastructure, which are taken into account in the site survey before deciding whether the infrastructure is ready to host mobile noble gas systems. Next, please.
Next slide.
Now, here we see pictures of the three CTBTU mobile systems, which are based on two different technologies. The French SPALAX deployment rapid, which means rapid deployment, and then the TXL, which means transportable xenon laboratory, which are based on sauna systems. And we have different generations of sauna, from sauna 1 for the PNNL system to sauna 2 and sauna 3 for the CTBTO systems. Next. The map here shows where the mobile background campaigns have been performed since 2008, and we see quite a lot of locations. Next slide. And here the first 6 campaigns were actually between 1 to a few weeks, which means short-range campaigns. Then the first long-term campaign started in 2012 in Jakarta, and in parallel Kuwait City, both using the CTBTO mobile systems. Then in 2014, the TXL system was moved from Jakarta to Takasaki, Japan, to be used, and it was used as a backup system while the IMS stations was being prepared for upgrade to certification. Then from Takasaki, the system was moved to Mutsu for a 3-month campaign from July to October 2014. Then back to Manado in Indonesia, and where we had another long-term campaign using the TXL system. This is using the EU-funded
systems.
Means. And then in addition to that, with the PNNL system, there was also a couple of campaigns, and this includes Burkina Faso and Jordan in 2013 and 14. Next. Here is now an illustration of a use case in Jakarta, where what we see on the photo is the stack release system, a stack monitoring system based on lanthanum bromide, and this was a collaboration work between CTBTO and the PNNL. So the system was installed at Inyuki, the current Inyuki, which was Batek at that time. And then the TXL system was installed around 20 kilometers away from the Batek medical isotope facility, which means this allowed detecting both the release at the medical isotope facility and then the detections at the TXL systems. And this allowed to advance our common understanding in terms of impact at the short range. And the work here was published by, it was a joint PNNL and CTBTO publication. Next. Here is now the map showing the locations of the currently ongoing campaigns in Japan, including the location which will host the SPALAX system in the southern part. So currently we have the system in Horonobi, another system in Mutsu, and along with the Ims Noble Gas Station. And when the GPX32 is installed, we will have a local dense network of 4 systems running in parallel. Here is now, in terms of timeline, the Horonobi system and the Mutsu were deployed in Q1 2018, which means so far we have 1 meteorological cycle at both sites. And then Fukuoka, the Spalax system is planned to be installed in Q4 this year. Next. So here we see in terms of system performance, the upper plot is for Horonoby, where the system was demonstrated a high level of data availability, whereas at Mutsu, the system was and still actually experiencing some malfunctioning issues, and the data is not being used since January 2019. Here is now the categorization results distribution based on 1 year of data. At Horonoby, it's a matter of around 74% of samples that have shown xenon detections. Then 3% at level C, which makes it only 20% in the green range. The detection rate is lower compared to at Mutsu compared to Horonoby. And here we also see a higher portion of samples that have been released without category because of data quality issues, as we mentioned in the previous slide. Now here we have the frequency distribution of xenon 133 at both Mutsu and Horonoby. So here we have more detections at Horonoby, which is now it's actually the total, and we don't see the stacked. It is not a stacked distribution. We don't see the different categories, but all categories included. But from the pattern of this distribution, we see a clear skewness at Horonoby, which is a synonym of a high rate of detections. Next slide.
So I think I take over here because Tammy just indicated to me we need to wrap up and make time for questions. And I just want to show this as an example of how we can make use of this high-density regional composition of systems. The method of possible source region that was applied in previous slides is not something that is set and cast in stone. There are still methodological alternatives. And this shows just 3 alternatives implemented in WebGrape, but there may be more. So we still need to refine the methods how we can understand a single release at an IMS station. We need, with a higher density configuration, we need more data of a single release with multiple samples, because possible source region we can only apply if we have multiple detections at different stations from the same source. And we can get much more multiple detections in short time with a high density network. This is why we have it. But the purpose is to be able to better understand IMS detections. So eventually these are temporarily, they will be removed, and then we continue using the methods that we sharpened and enhanced with the mobile system installations at IMS stations. And there's a lot of future work to be done, and we invite every scientist to support and contribute. Data will be available. So this is an opportunity for cooperation, but we want to keep time now for questions instead of talking longer.
Yeah, if you could put the questions on the page, turn the lights on in the audience so that we can see you. And before we start with, I think there's one question of relevance that we could answer that was posted 6 minutes ago, but is there anyone on the floor who would like to come forward and ask a question or provide a comment or thought based on what you've heard today? Right up here in the front row, please.
Thank you, commending the presentation. Have you ever, in order to find out the background apart from the case that the medical isotope production might be because of the shutdown, refueling might have an effect in your background. Also, they might have been changing the degree of the production, changing the filter of the stack. Those kind of things is only possible when you ask the operators of that country X, what have you done during this last point, so that this will have an impact. Of course, when it is shut down, everybody knows and you can find out. But there are other things that it is changing the production when it is mobile fission moly or the iodine, whatever, this all will have impact on your results. Have you done so? Thank you.
We are not asking. We are open to receive voluntary information. Our doors are open. And then we can understand, is this information we can share with state signatories, and eventually we can use only information that is openly available and can be shared with all state signatories. In the exploratory experimental phase that we are currently in, we can accept also data from stack release measurements, and we make them available on the VDEC platform also for experts who want to share these studies. And we did this already with what we call an ATM challenge, and we used from the UNSTO facility over a period of time the release data that they measured at their stack. We gave them to how many? 14 different meteorological organizations who signed a VDEC confidentiality agreement with us, and this competition or challenge was conducted to compare results of how well we can predict the detections at IMS stations, and even at 13,000 kilometers distance, I don't remember exactly, but at a long distance, the short peak that we saw there was explained with the release from UNSTO in this study.
Maybe I will add that there is a publication which describes in detail all our results, so it's available.
Then maybe talking about VDEC. So the data from both IMS stations and the mobile campaigns are also available to the community based on $0 contract. So this is also a way to make good use of the data by the wider scientific and in addition to the monitoring community. Thank you.
Ted.
Hi, thank you, Tammy, and thank you, Martin. Just to refer to an answer to a very direct answer to the previous question, this is that information has been publicized and published, and a great example was following one of the WASMIP workshops. It was identified that one of the producers was using a certain type of connector in their facility, and they switched to using a stainless steel connector. That simple thing reduced their emissions by about a factor of 2. So those things are known, and in our workshops we explore those very easy fixes, and occasionally they do happen. Thank you.
Any other questions from anyone in the audience? Okay, we have one online question that's fairly new and rated highly. How well can we categorize releases from known or common civil nuclear sources, and what challenges are presented by the unknown emissions profiles of emerging technologies?
Yeah, I can say something. Okay. Every type of facility has a typical profile of isotope ratios. So those facilities that have longer times of before they release, decay times before they release the emissions, of course, the isotope ratios have decayed, and so if we can look at the distribution of releases that are reported, and then compare this, of course, allowing for decay through transport time, compare this with the detections that we have. Whether unknown emission profiles of emerging technologies, well, if the technology is emerging, then we can rely on studies that calculate, simulate the expected releases. And of course, we are keeping our eyes open for the literature. And I saw also here presentations about something like this at this conference. So of course, this can all be taken into consideration.
All right, we've hit our time. I know Jolanta needs to leave to go finish the ranking of the posters for our awards ceremony starting at 11. We can stay available to you if anyone wants to come forward and have discussion, but maybe we should cut the panel discussion off at this time for others who need to leave. So thank you very much, and a huge shout out and thank you to Flora Trillo, who helped us with our technical background and competency. We're very appreciative. Okay, thank you everyone.